Cardano is a project that began in 2015 as an effort to change the way cryptocurrencies are designed and developed. The overall focus beyond a particular set of innovations is to provide a more balanced and sustainable ecosystem that better accounts for the needs of its users as well as other systems seeking integration. In the spirit of many open-source projects, Cardano did not begin with a comprehensive roadmap or even an authoritative white paper. Rather, it embraced a collection of design principles, engineering best practices and avenues for exploration. These include the following: separation of accounting and computation into different layers, implementation of core components in highly modular functional code, small groups of academics and developers competing with peer-reviewed research, heavy use of interdisciplinary teams including early use of InfoSec experts, fast iteration between white papers, implementation and new research required to correct issues discovered during review, building in the ability to upgrade post-deployed systems without destroying the network, development of a decentralized funding mechanism for future work, a long-term view on improving the design of cryptocurrencies so they can work on mobile devices with a reasonable and secure user experience, bringing stakeholders closer to the operations and maintenance of their cryptocurrency, acknowledging the need to account for multiple assets in the same ledger, abstracting transactions to include optional metadata in order to better conform to the needs of legacy systems, learning from the nearly 1,000 altcoins by embracing features that make sense, adopt a standards-driven process inspired by the Internet Engineering Task Force using a dedicated foundation to lock down the final protocol design, explore the social elements of commerce, find a healthy middle ground for regulators to interact with commerce without compromising some core principles inherited from Bitcoin. From this unstructured set of ideas, the principals working on Cardano began both to explore cryptocurrency literature and to build a tool set of abstractions. The output of this research is IOHK's extensive library of papers, numerous survey results such as this recent scripting language overview as well as an ontology of smart contracts, and the ScoreX project. Lessons yielded an appreciation for the cryptocurrency industry's unusual and at times counterproductive growth. First, unlike successful protocols such as TCP/IP, there is little layering in the design of cryptocurrencies. There has been a desire to preserve a single notion of consensus around facts and events recorded in a single ledger, regardless of whether it makes sense. For example, Ethereum has encumbered enormous complexity attempting to become a universal world computer, but suffers from trivial concerns potentially destroying the system's ability to operate as a store of value. Should everyone's program be a first-class citizen regardless of its economic value, cost to maintain, or regulatory consequences? Second, there is little appreciation for prior results in mainstream cryptographic research. For example, BitShares delegated proof-of-stake could have easily and reliably generated random numbers using coin tossing with guaranteed output delivery, which is a technique known since the 1980s. See the seminal paper by Rabin and Ben-Or. Third, most altcoins, with a few notable exceptions such as Tezos, have not made any accommodation for future updates. The ability to successfully push a soft or hard fork is pivotal to the long-term success of any cryptocurrency. As a corollary, enterprise users cannot commit millions of dollars worth of resources to protocols where the roadmap and actors behind them are ephemeral, petty or radicalized. There needs to be an efficient process through which social consensus can form around a vision for evolving the underlying protocol. If this process is enormously burdensome, fragmentation could break the community apart. Finally, money is ultimately a social phenomenon. In the effort to anonymize and disintermediate central actors, Bitcoin and its contemporaries have also discarded a need for stable identities, metadata and reputation in commercial transactions. Adding these data through centralized solutions removes the auditability, global availability and immutability, which is the entire point of using a blockchain. Legacy financial systems such as those composed of Swift, FIX and ACH are rich in transactional metadata. It is not enough to know how much value moved between accounts. Regulation often requires the attribution of actors involved, compliance information, reporting suspicious activity, and other records and actions. In some cases, the metadata is more important than the transaction. Hence, it seems reasonable to infer that the manipulation of metadata could be as harmful as counterfeiting currency or rewriting transaction history. Making no accommodation for actors who want to voluntarily include these fields seems counterproductive to mainstream adoption and consumer protection. Sojourn's End. The aggregation of our principled exploration of the cryptocurrency space is two collections of protocols, respectively, a provably secure proof of stake, 1, 2, based cryptocurrency called the Cardano Settlement Layer, CSL, and a set of protocols called the Cardano Computation Layer, CCL. Our design emphasis is to accommodate the social aspects of cryptocurrencies, build in layers by separating the accounting of value from complex computation and address the needs of regulators within the scope of several immutable principles. 1. Furthermore, where it is sensible, we attempt to vet proposed protocols through peer review and check code against formal specifications. Proof of stake. Using proof of stake for a cryptocurrency is a hotly debated design choice. However, because it adds a mechanism to introduce secure voting, has more capacity to scale, and permits more exotic incentive schemes, we decided to embrace it. Our proof-of-stake protocol is called Ouroboros, and it has been designed by an extremely talented team of cryptographers from 5 academic institutions, 2 led by Professor Orgelis Kaiaias of the University of Edinburgh. The core innovation it brings beyond being proven secure using a rigorous cryptographic model is a modular and flexible design that allows for the composition of many protocols to enhance functionality. This modularity allows for features such as delegation, sidechains, subscribable checkpoints, better data structures for light clients, different forms of random number generation, and even different synchronization assumptions. As a network develops from having thousands to millions and even billions of users, the requirements of its consensus algorithm will also change. Thus, it is vital to have enough flexibility to accommodate these changes and thereby future-proof the heart of a cryptocurrency. Social elements of money. Cryptocurrencies are a prime example of the social component of money. When restricting analysis solely to technology, there is little difference between Bitcoin and Litecoin, and even less so between Ethereum and Ethereum Classic. Yet, both Litecoin and Ethereum Classic maintain large market capitalizations and robust, dynamic communities as well as their own social mandates. It can be argued that a large part of the value of a cryptocurrency is derived from its community, the way it uses the currency, and its level of engagement in the currency's evolution. Furthering the thought, currencies such as Dash have even integrated systems directly into the protocol to engage their community in deciding what should be a priority to develop and fund. The vast diversity of cryptocurrencies also provides evidence for their social elements. Disagreements about philosophy, monetary policy, or even just between the core developers led to fragmentation and forks. Yet unlike their cryptocurrency counterparts, fiat currencies of superpowers tend to survive political shifts and local disagreements without a currency crisis or mass exodus. Therefore, it seems that there are elements of legacy systems that are missing from the cryptocurrency industry. We argue, and have inculcated into the Cardano roadmap, that users of a protocol need incentives to understand the social contracts behind their protocol and have the freedom to propose changes in a productive way. This freedom extends to every aspect of a value exchange system, from deciding how markets should be regulated to which projects should be funded. Yet it cannot be brokered through centralized actors nor requires some special credential that could be co-opted by a well-funded minority. Cardano will implement a system of overlay protocols built on top of CSL to accommodate the needs of its users. First, regardless of the success of a crowd sale to bootstrap development, funds will eventually dissipate. Hence, Cardano will include a decentralized trust refunded from monotonically decreasing inflation and transaction fees. Any user should be eligible to request funds from the trust by a ballot system, and the stakeholders of CSL vote on who becomes a beneficiary. The process creates a productive feedback loop seen in other cryptocurrencies with treasury trust systems, such as Dash. By starting a conversation about who should and should not be funded, funding discussions force a relation of long and short-term goals, the cryptocurrency's social contract, priorities, and the belief in value creation with particular proposals. This conversation means that the community is constantly evaluating and debating its beliefs against possible roadmaps. Second, our hope is that Cardano will eventually include a formal, blockchain-based system to propose and vote on both soft and hard forks. Bitcoin with its block size debate, Ethereum with the DAO fork, and many other cryptocurrencies besides have endured long-standing and, in frequent cases, unresolved arguments over the technical and moral direction of the codebase. It can and should be argued that many of these disagreements, and the fracturing of the community that results when action is taken, are a direct result of a lack of formal processes for debating change. Where does one go to convince Bitcoin users to adopt segregated witness? How should the core developers of Ethereum measure community sentiment for bailing out the DAO? If the community fractures, is the cryptocurrency damaged beyond repair? In the worst cases, moral authority to act could simply devolve to whoever has the developers, infrastructural relationships and money, not the best wishes of the vast majority of the community. Furthermore, if a large portion of the community is inaccessible or disengaged due to bad incentives then how can one truly know if their acts are legitimate? Proposed cryptocurrencies such as Tezos provide an interesting model to examine where a cryptocurrency protocol is treated like a constitution containing 3 sections: transaction, consensus and network, with a set of formal rules and process to update the constitution. Yet there remains much work to be done with incentives and over how exactly to model and change a cryptocurrency with a formal language, the use of formal methods, machine-understandable specifications and merging a treasury with this process for financial incentives are being explored as possible avenues for inspiration. Ultimately, just the ability to propose a protocol change in a transparent, censorship-free way with blockchain-based voting should improve the process, even if more elegant solutions cannot be designed. Designing in layers. Cardano settlement layer. When designing great protocols and languages, one should not look to the future, but rather to the past. History provides a litany of examples of great ideas that are perfect on paper, yet somehow have not survived, such as the open systems interconnection standards. History also provides happy accidents that have endured from TCP/IP to JavaScript. Some principles extracted from a historical view are the following. You cannot predict the future, so build in wiggle room. Complexity is nice on paper, but simplicity usually wins. Too many cooks spoil the broth. Once a standard is set, it will probably stick around, regardless of whether it is suboptimal. Bad ideas can actually evolve into pretty good ones if there is a will. Cardano is a financial system that accepts its social nature. There will be a tremendous need for flexibility and the ability to address arbitrary complexity in a particular user's transaction. If successful, there will be a need for tremendous computational, storage and network resources to accommodate millions of concurrent transactions. Yet we do not have a digital, decentralized Robin Hood to take from the rich nodes and give to the poor ones in order to achieve a fair network. Nor do we have the luxury of trusting human beneficence to altruistically sacrifice for the greater good of the network. Therefore, Cardano's design borrows from TCP/IP the concept of separation of concerns. Blockchains are ultimately databases ordering facts and events with guarantees about timestamps and immutability. In the context of money, they order ownership of assets. Adding complex computation by storing and executing programs is an orthogonal concept. Do we want to know how much value went from Alice to Bob? Or do we want to get involved in figuring out the whole story behind the transaction and deciding how much to send? It is incredibly tempting to choose the latter, as Ethereum has done, because it is more flexible, but it violates the design principles above. Figuring out the story means that a single protocol has to be able to understand arbitrary events, script arbitrary transactions, permit arbitration in cases of fraud, and even potentially reverse transactions when new information is made available. Then one has to make difficult design decisions about what metadata to store for each transaction. What elements of the story behind Alice and Bob's transaction are relevant? Are they relevant forever? When can we throw away some data? Does doing so violate the law in some countries? Furthermore, some computation is private in nature. For example, when calculating the average salary of workers in an office, we would not necessarily want to leak how much each person makes. But what if every computation is publicly known? What if this publicity biases execution in order to harm outcome? Thus, we have chosen the position that the accounting of value should be separated from the story behind why the value is moved. In other words, separation of value from computation. This separation does not mean that Cardano will not support smart contracts. On the contrary, by making this separation explicit, it permits significantly more flexibility in the design, use, privacy and execution of smart contracts. The value ledger is called the Cardano settlement layer, CSL, as the purpose is to account for value. The roadmap has the following goals: support 2 sets of scripting languages, one to move value and another to enhance overlay protocol support. Provide support for KMZ sidechains 5 to link to other ledgers. Support multiple types of signature including quantum-resistant signatures for higher security. Support multiple user-issued assets. Achieve true scalability, meaning as more users join, the capabilities of the system increase. Scripting. Starting with a scripting language, transactions between addresses in a ledger require some form of a script to execute and be proven valid. Ideally, one would not want Eve to access Alice's money, nor would one want a poorly designed script to accidentally send value to a dead address, making the funds irretrievable. Systems such as Bitcoin provide an extremely inflexible and draconian scripting language that is difficult to program bespoke transactions in, and to read and understand. Yet the general programmability of languages such as Solidity introduce an extraordinary amount of complexity into the system and are useful to only a much smaller set of actors. Therefore, we have chosen to design a new language called Simon 6 in honor of its creator Simon Thompson and the creator of the concepts that inspired it, Simon Peyton Jones. Simon is a domain-specific language that is based upon composing contracts, an adventure in financial engineering. The principal idea is that financial transactions are generally composed from a collection of foundational elements. 7. If one assembles a financial periodic table of elements, then one can provide support for an arbitrarily large set of compound transactions that will cover most, if not all, common transaction types without requiring general programmability. The primary advantage is that security and execution can be extremely well understood. Proofs can be written to show correctness of templates and exhaust the execution space of problematic transaction events, such as the creation of new money out of thin air or transaction malleability. Second, one can leave in extensions to add more elements by way of soft forks if new functionality is required. That said, there will always be a need to connect CSL to overlay protocols, legacy financial systems, and special-purpose servers. Thus we have developed Plutus as both a general-purpose smart contract language and also a special-purpose DSL for interoperability. Plutus is a type functional language based on concepts from Haskell, which can be used to write custom transaction scripts. For CSL, it will be used for complex transactions required to add support for other layers we need to connect, such as our sidechain scheme. Sidechains. With respect to sidechains, Cardano will support a new protocol developed by Caius, Miller and Zindris, KMZ sidechains, based upon prior results from proofs of work. The particular design is beyond the scope of this paper. However, the concept allows for the secure and non-interactive movement of funds from CSL to any Cardano computation layer or other blockchain supporting the protocol. KMZ sidechains are the key to encapsulating complexity, ledgers with regulatory requirements, private operations, robust scripting languages and other special concerns are effectively black boxes to CSL, yet the CSL user will gain certain guarantees about accounting and the ability to recall funds once computation is complete. Signatures. In order to securely move value from Alice to Bob, Alice needs to prove she has the right to move the funds. The most direct and reliable way of accomplishing this task is to use a public key signature scheme where funds are connected to a public key and Alice controls an associated private key. There are hundreds of possible schemes with different security parameters and assumptions. Some rely upon mathematical problems connected to elliptic curves, whereas others are connected to exotic concepts using lattices. The abstract goal is always the same. There exists a hard problem that cannot be solved unless someone has a secret piece of knowledge. The holder of this piece of knowledge is said to be the owner of the keeper and should be the only entity that has the ability to use it. There are two groups of concerns a cryptocurrency faces with choosing a signature scheme. First, there is the long-term security durability of the scheme itself. Some cryptographic schemes used in the 1970s and 1980s such as DES have been broken. The period over which the scheme should be expected to survive must be decided upon. Second, there are many enterprises, governments and other institutions that have preferred, or in some cases, mandated the use of a particular scheme. For example, the NSA maintains the Suite B protocol set. There are standards from ISO and even W3C workgroups on cryptography. If a cryptocurrency chooses a single signature scheme, it is forced to accept that the scheme could be broken at some point in the future and at least one entity cannot use the cryptocurrency due to legal or industry restrictions. Yet a cryptocurrency cannot support every signature scheme as this would require every client to understand and validate each scheme. For Cardano, we decided to start with using elliptic curve cryptography, the ED25519 curve in particular. We also decided to enhance the existing libraries by adding support for HD wallets using Dr. Dmitry Kovaratovich and JSON Law Specification 8. This said, Cardano will support more signature schemes in the future. In particular, we are interested in integrating BLIS-B to add quantum computer-resistant signatures to our system. We are also interested in adding SEC 256K1 to enhance interoperability with legacy cryptocurrencies such as Bitcoin. Cardano has been designed with special extensions that will allow us to add more signature schemes through a soft fork. They will be added as needed and during major updates planned in the Roadmap 9. User-issued assets, UIAS. Early in Bitcoin's history, protocols were quickly developed to allow users to issue assets that piggybacked on Bitcoin's accounting system in order to track multiple currencies concurrently. These protocols were not natively supported by the Bitcoin protocol, but implemented through clever hacks. In the case of Bitcoin overlays such as colored coins and Mastercoin, now called Omni, light clients are forced to rely on trusted servers. Also, transaction fees still have to be paid in Bitcoins. These properties combined with a single pipeline for transaction approval make Bitcoin suboptimal for multi-asset accounting. In the Ethereum case using the ERC20 standard, there is more feature richness. However, transaction fees still require Ether. Furthermore, the Ethereum network is having difficulty scaling to the needs of all the issued ERC20 tokens. The fundamental problem can be broken into three parts: resources, incentives and concern. With respect to resources, adding an entirely new currency to the same ledger means one has two independent UTXO, unspent transaction inputs, sets sharing the bandwidth, mempool and block space. Consensus nodes responsible for embedding transactions of these currencies need an incentive for doing so, and not every user of a cryptocurrency will or should care about a particular entity's currency. Given these problems, the benefits are tremendous as the primary token of a multi-asset ledger can effectively serve as a bridge currency allowing for decentralized market making. Special purpose assets could be issued to provide additional utility such as value-stable assets like Tether or MakerDAO that are useful for lending and remittance applications. Given the challenges, Cardano has adopted a pragmatic approach to multi-asset accounting, building in stages. The first challenge is designing the necessary infrastructure to support the demands of thousands of UIAs. Namely, the following advancements are necessary. Special purpose authenticated data structures to permit the tracking of a very large UTXO state. The ability to have a distributed mempool to hold a huge set of pending transactions. Blockchain partitioning and checkpoints to permit a huge global blockchain. An incentive scheme that rewards consensus nodes for including different sets of transactions. A subscription mechanic that allows users to decide which currencies they want to track. Strong security guarantees that UIAs enjoy similar security as the native asset. Support for decentralized market making to improve liquidity between UIA and the primary token. Our preliminary efforts for finding the right authenticated data structure have resulted in a new type of AVL plus tree jointly developed by Leo Reason, IOHK and Waves. More research is required, but it is a foundational advancement that will be included in a later version of Cardano. A distributed mempool could be implemented using Stanford University's RAM Cloud protocol. Experiments will begin in Q3 of 2017 to study its integration into Cardano's consensus layer. The remaining topics are interconnected and covered by ongoing research. We expect, subject to research results, to include a protocol into Cardano for UIAs during the Basho of CSL release in 2018. Scalability. Distributed systems are composed of a set of computers, nodes, agreeing to run a protocol or suite of protocols to accomplish a common goal. This goal could be sharing a file as defined by the BitTorrent protocol or folding a protein using folding at home. The most effective protocols gain resources as nodes join the network. A file hosted by BitTorrent, for example, can be downloaded much faster on average if many peers are concurrently downloading it. The speed increases because the peers provide resources while also consuming them. This characteristic is what one typically means when stating a distributed system scales. The challenge with the design of all current cryptocurrencies is that they actually are not designed to be scalable. Blockchains, for example, are usually an append-only linked list of blocks. The security and availability of a blockchain protocol relies upon many nodes possessing a full copy of the blockchain data. Thus, a single byte of data must be replicated among n nodes. Additional nodes do not provide additional resources. This result is the same for transaction processing and the gossiping of messages throughout the system. Adding more nodes to the consensus system does not provide additional transaction processing power. It just means more resources have to be spent to do the same job. More network relaying meaning more nodes have to pass the same messages to keep the whole network in synchronization with the most current block. Given this topology, cryptocurrencies cannot scale to a global network on par with legacy financial systems. In contrast, legacy infrastructure is scalable and has orders of magnitude for more processing and storage power. Adding a specific point, Bitcoin is a very small network relative to its payment peers, yet struggles to manage its current load. Our scalability goals for Cardano are greatly aided by our consensus algorithm. Ouroboros permits a decentralized way to elect a quorum of consensus nodes, which in turn can run more traditional protocols developed over the last 20 years to accommodate the needs of large infrastructure providers such as Google and Facebook 10. For example, the election of a quorum for an epoch means we have a trusted set of nodes to maintain the ledger for a specific time period. It is trivial to elect multiple quorums concurrently and partition transactions to different quorums. Similar techniques could be applied for network propagation and also sharding the blockchain itself into unique partitions. In our current roadmap, scaling methods will be applied to Ouroboros starting in 2018 and continue to be a focus in 2019 and 2020. Cardano computation layer. As mentioned previously, there are two components of a transaction: the mechanism to send and record the flow of tokens and the reasons as well as conditions behind moving tokens. The latter can be arbitrarily complex and involve terabytes of data, multiple signatures and special events occurring. The latter can also be remarkably simple with a single signature pushing value to another address. The challenge behind modeling the reasons and conditions of value flow is that they are immensely personal to the entities involved in the most unpredictable of ways. Lessons from contract law paint an even more problematic picture where the actors themselves might not even be aware that the transaction does not match commercial reality. We generally call this phenomenon the semantic gap. 11. Why should one build a cryptocurrency chasing an endless layer of complexity and abstraction? It seems Sisyphean in nature and naive in practice. Furthermore, each abstraction embraced has both legal and security consequences. For example, there are numerous activities online that are universally deemed illegal or scorned, such as the trafficking of child pornography or the selling of state secrets. By deploying robust decentralized infrastructure, one is now providing a channel for this activity to occur with the same censorship resistance that normal commercial transactions enjoy. It is legally unclear if the consensus nodes of the network, which have the incentive to become more federated over time to promote efficiency, would be held accountable for the content they host. Prosecution of tour operators. The brutal treatment of Silk Road's operator and the lack of overall legal clarity behind legal protections of protocol participants leaves an uncertain road. There is no lack of imagination of what else a sufficiently advanced cryptocurrency could enable. See the ring of judges. Is it reasonable to force all users of a cryptocurrency to endorse or at least enable the worst acts and conduct of the web? Unfortunately, there are no clear answers that provide insight to a cryptocurrency designer. It is more about picking a position and defending its merit. The advantage that both Cardano and Bitcoin have is that we have chosen two separate concerns to layers. With Bitcoin, there is rootstock. With Cardano, there is the Cardano computation layer. The kinds of complex behavior that would enable the acts elaborated previously cannot run on CSL. They require the ability to run programs written in a Turing-complete language and some form of gas economics to meter computation. They also require consensus nodes willing to include the transactions in their blocks. Thus, a functionality restriction could reasonably protect users. So far, most established governments have not taken the position that the use or maintenance of a cryptocurrency is an illegal act. Hence, the vast majority of users should be comfortable maintaining a ledger that is comparable in capability with a digital payment system. When one wants to extend capability, there are two possibilities. It is enabled by a private collective of like-minded individuals and ephemeral in nature, for example, a poker game, or it is enabled by a ledger of comparable capabilities as Ethereum. In both cases, we have chosen outsourcing the event to another protocol. In the case of a private, ephemeral event, it is reasonable to avoid the blockchain paradigm entirely, but rather restrict efforts towards a library of special-purpose MPC protocols that can be invoked when desired by a group of like-minded participants. The computations and activities are coordinated in a private network and reference CSL only as a trusted bulletin board and a message-passing channel when necessary. The key insight in this case is that there is consent, encapsulation of liability and privacy. CSL is being used as a digital commons for users to meet and communicate, like a park would host a private event, but does not provide any special accommodations or facilitation. Furthermore, the use of special-purpose MPC will enable low-latency interaction without the need for blockchain load. Thus, it improves the scale of the system. Cardano's research efforts towards this library are centralized at our Tokyo Tech Laboratory with some assistance from scientists abroad. We call the library Tartaglia after a fellow mathematician as well as contemporary of Cardano and expect the first iteration to be available in Q1 of 2018. In the second case, one needs a blockchain with a virtual machine, a set of consensus nodes and a mechanism to enable communication between the two chains. We have begun the process of rigorously formalizing the Ethereum virtual machine using the K-Framework 12 in partnership with a team from the University of Illinois. The result of this analysis will inform the most optimal way to design a replicated and eventually distributed virtual machine 13 with clear operational semantics and strong guarantees of correct implementation from the specification. In other words, the VM actually does what the code tells it to do with the security risks minimized. There are still unresolved questions about the gas economics proposed by Ethereum and how it relates to work such as Jan Hoffman et al.'s resource-aware ML and the broader study of resource estimation for computation. We are also curious about the level of language independence of the virtual machine. For example, the Ethereum project has expressed desire for transition from their current VM to WebAssembly. The next effort is in developing a reasonable programming language to express stateful contracts that will be called as services by decentralized applications. For this task, we have chosen both the approach of supporting the legacy smart contract language Solidity for low assurance applications and developing a new language called Plutus for higher assurance applications requiring formal verification. Like the Solidity-based Zeppelin project, IOHK will also develop a reference library of Plutus code for application developers to use in their project. We will also develop a specialized set of tools for formal verification inspired by work from UCSD's Liquid Haskell project. In terms of consensus, Ouroboros was designed in a sufficiently modular fashion to support smart contract evaluation. Hence, both CSL and CCL will share the same consensus algorithm. The difference is that Ouroboros can be confirmed to permit both permissioned and permissionless ledgers via token distribution. With CSL, ADA has been distributed by a token-generating event to purchasers throughout Asia who will eventually resell on a secondary market. This means that CSL's consensus algorithm is controlled by a diverse and increasingly more decentralized set of actors or their delegated assigns. With CCL, it is possible to create a special-purpose token held by delegates of that ledger who could be regulated entities, thereby creating a permissioned ledger. The flexibility of this approach allows for different instances of CCL to materialize with different rules about the evaluation of transactions. For example, gambling activities could be restricted unless KML data is present simply by blacklisting non-attributed transactions. Our final design focuses on adding trusted hardware security modules, HSM, to our protocol stack. These are two enormous advantages when introducing these capabilities into the protocol. First, HSMs provide massive boosts in performance 14 without introducing security concerns beyond trusting the vendor. Second, through the use of sealed glass proofs, SGP, HSMs can provide assurances that data can be verified and then destroyed without being copied or leaked to malicious outsiders. Focusing on the second point, SGPs could have a revolutionary impact upon compliance. Ordinarily, when a consumer provides personally identifiable information, PII, to authenticate identity or prove the right to participate, this information is handed to a trusted third party with the hope it will not act maliciously. This activity is intrinsically centralized. The data provider loses control over their PII and is also subject to various regulations based on jurisdiction. The ability to select a set of trusted attesters and then warehouse PII in a hardware enclave means that any actor with a sufficiently capable HSM will be able to verify facts about an actor in an unforgeable way without the verifier knowing the identity of the actor. For example, Bob is not a U.S. citizen, Alice is an accredited investor, James is a U.S. taxpayer and one should send taxable profits to account X. Cardano's HSM strategy will be to attempt implemented specialized protocols over the next 2 years using Intel SGX and ARM TrustZone. Both modules are built into billions of consumer devices from laptops to cell phones and require no additional effort on the consumer side to use. Both are also heavily vetted, well-designed and based upon years of iteration from some of the largest and best-funded hardware security teams. Regulation. The harsh reality of all modern financial systems is that as they scale, they accumulate a need, or at least a desire, for regulation. This outcome is generally the result of recurrent collapses due to the negligence of some actor or cabal of actors in a marketplace. For example, The Knickerbocker crisis of 1907 resulted in the creation of the Federal Reserve System in 1913 as a lender of last resort. Another example is the excesses of the 1920s in the United States that resulted in a terrible financial collapse, the Great Depression. This collapse yielded the creation of the Securities Exchange Commission in 1934 in order to prevent a similar event or at least hold bad actors accountable. One can reasonably debate the need for, scope and efficacy of regulation, but one cannot deny its existence and the zeal with which major governments have enforced it. However, the challenge all regulators face as the world globalizes and cash becomes digital is two-pronged. First, which set of regulations should be supreme when dealing with a collection of jurisdictions? The antiquated notion of Westphalian sovereignty melts when a single transaction can touch 36 countries in under a minute. Should it simply be whomever wields the most geopolitical influence? Second, improvements in privacy technology have created a digital arms race where it will become increasingly more difficult to even understand who has participated in a transaction, much less who owns a particular store of value. In a world where millions of dollars of assets can be controlled with nothing more than a secretly held 12-word mnemonic 15, how do you enforce effective regulation? Like all financial systems, the Cardano protocol must have an opinion in its design over what is fair and reasonable. We have chosen to divide between individual rights and the rights of a marketplace. Individuals should always have sole access to their funds without coercion or civil asset forfeiture. This right has to be enforced because not all governments can be trusted not to abuse their sovereign power for the personal gain of corrupt politicians. As seen in Venezuela and Zimbabwe, cryptocurrencies have to be engineered to the lowest common denominator. Second, history should never be tampered with. Blockchains provide a promise of immutability. Introducing the power to roll back history or alter the official record introduces too much temptation to change the past in order to benefit a particular actor or actors. Third, the flow of value should be unrestricted. Capital controls and other artificial walls diminish human rights, outside of the futility of attempting to enforce them. 16. In a global economy with many citizens in the least developed nations traveling outside of their jurisdiction to find a living wage, restricting capital flows usually ends up harming the poorest in the world. These principles stated, markets are distinctly different from individuals. While the designers of Cardano believe in individual rights, we also believe that markets have the right to openly state their terms and conditions, and if an individual agrees to do business within this market, then they must be held to those standards for the sake of integrity of the entire system. The challenge has always been cost and practicality of enforcement. Small, multi-jurisdictional transactions are simply too expensive in legacy systems to provide high assurance of recourse in the event of fraud or a commercial dispute. When one sends their wire transfer to the Nigerian Prince 17, it is usually too expensive to try to get one's funds back. For Cardano, we feel we can innovate on 3 levels. First, through the use of smart contracts, the terms and conditions of commercial relationships can be better controlled. If all assets are digital and can be solely expressed on CSL, strong guarantees of fraud-free commerce can be gained. Second, the use of HSMs to provide an identity space where PI is not leaked but yet used to authenticate and credential actors should provide a global reputation system and allow for much lower-cost regulated activities to be conducted, such as online gaming with automated tax compliance or decentralized exchanges. Finally, in Cardano's roadmap is the creation of a modular regulation DAO that can be customized to interact with user-written smart contracts in order to add mutability, consumer protection and arbitration. The scope of this project will be outlined in a later paper. What is the point of all of IT? Cardano has been a marathon project involving feedback from hundreds of the brightest minds inside and outside of the cryptocurrency industry. It involves tireless iteration, the active use of peer review, and shameless theft of great ideas when uncovered. The remaining sections each cover a particular aspect of focus we have decided is a core component of our project. Some were selected due to a desire to improve the overall best practices of the space, whereas others are specific to Cardano's evolution. While no project can cover every goal or satisfy every user, our hope is to provide a vision for what a self-evolving financial stack should look like for jurisdictions that lack them. The ultimate reality of cryptocurrencies is not that they will disrupt the existing legacy financial systems. Legacy financial systems are always capable of absorbing change and maintaining their form and function. Rather, one ought to look to places where it is simply too expensive to deploy the existing banking system, where many live on less than a few dollars a day, have no stable identity and credit is impossible to find. In these places, The power to bundle a payment system, property rights, identity, credit and risk protection into a single application running on a cell phone is not just useful, it is life-changing. The reason we are building Cardano is that we feel we have a legitimate shot at delivering, or at least advancing, this vision for the developing world. If we can change the way cryptocurrencies are designed, evolved and funded, then there is a great accomplishment. Footnotes. 1. See Regulation section for list. 2. University of Connecticut, University of Athens, University of Edinburgh, Aarhus University, Tokyo Institute of Technology. 3. This is also known as a treasury system. 4. See Rational Ignorance. 5. See Non-Interactive Proofs of Proof of Work from Kaius, Zindras and Miller. 6. Specifics will be released in an upcoming specification. The full language will be supported in the Shelley CSL release planned for Q4 of 2017. 7. Project Actus has an in-depth elaboration. 8. This is the documentation for Cardano's HD wallet implementation. We believe Cardano is the first cryptocurrency to support DED 25,519 HD wallets. 9. See CardanoRoadmap.com. 10. There are also other independently researched protocols attempting to achieve the same ends such as Elastico and Bitcoin. 11. Loilu et al. Discuss the gap in their recent paper on making smart contracts smarter. 12. Invented by Professor Grigorosu et al. K is a universal framework for language-independent machine executable semantics. Prior to our work, it has been used to model C, Java and JavaScript. 13. Meaning that different consensus nodes run different smart contracts, also known as state sharding. 14. See Scaling Bitcoin with Secure Hardware from Cornell University. 15. See BIP 39. 16. As an example of a countermeasure to capital flow, see the Hawala banking system. 17. See Advance Fee Scam.